Okay, so good morning. By way of introduction, I'm Chiara MF Mingarelli. The Italians will know what MF stands for. The rest of you, it's exactly what you think it is. All right, so today you're going to learn about pulsar timing arrays and how they work. We're going to go across the gravitational wave spectrum, starting from very low gravitational wave frequencies, going up to LIGO to just situate you in this landscape. And then I'll also try to retrain your intuition that you've probably learned for LIGO or for LISA, and try to give you a sense of how things work with pulsar timing arrays. I'm going to walk you through results from the NANOGrav 15-year data set and tell you why we were so excited in 2023 to report evidence of the gravitational wave background. And then I'm going to tell you where we're going next. We'll probably find signs of individual supermassive black hole binaries, but how do we know that they're real? And should these black hole binaries induce things like anisotropy in the gravitational wave background? How can we use tools from cosmology to search for that anisotropy? Are there other things that we should be looking for, et cetera? We'll touch on signs of discreteness in the gravitational wave background that can tell us whether or not the background is astrophysical or cosmological. And then we'll look at the consequences of that. So if the background is astrophysical, there should be some sort of anisotropy in it. The cosmologists in the room will think anisotropy is 1 part in 10 to the 5. That's not a big deal. You'll never get there. It's only true for any kind of cosmological background. For astrophysical backgrounds, the levels of anisotropy can be of around 10% of the monopole. So the anisotropies are really huge for astrophysical sources. So as a sneak peek for people who are already familiar with gravitational waves, I used to give this kind of update bar on where we're at and where we're going. And so the gravitational wave background was always 5 to 10 years away until it was now. And so now we are 0 years away from having evidence of the background. In fact, maybe it's -2 at this point, which is kind of cute. The next thing that we expect to find is evidence of continuous gravitational waves. And so those come from individual supermassive black hole binary systems. And then those individual binaries should induce some level of anisotropy in the background. And that anisotropy is typically weaker. And so that'll likely come after the detection of the first continuous waves. But we'll see. It depends on how far away they are, if there's extra clustering, et cetera. Okay, and then after we find that, LISA will fly. And hopefully LISA will be able to benefit from everything we've learned about the first supermassive black hole binaries that we can carry through to the LISA band. So before we get started anymore, I just wanted to ask the NANOGrav members to stand up so you can identify who they are. So Chinyuan and Bjorn are my students. They are here. And then I know there's Emiko. Great, fantastic, and wonderful. So these are the NANOGrav members here. And then if you work on pulsar timing arrays, there's Matthias, there's Bruce. Yeah. You guys know who Matthias is. He can sit down. And then Neil, of course. Do I have to find you guys all? The lights are very bright. Great. So it's not only me who's an expert here, but there's a lot of students that are working in the field, and then some of us that are a little bit more senior. Okay, great. So we'll start with an overview of the gravitational wave spectrum. So I'm going to focus today on pulsar timing arrays, which are very low frequencies. Today is an overview of the whole field. And then my next 2 lectures are going to be more technical. One is deriving the overlap reduction function, which we call the Hellings and Downs curves for an Einsteinian gravitational wave background that's also isotropic. And then the second thing I'll derive for you is the characteristic strain. But today, just take for granted that these things make sense, and I'll go into more technical detail in Blackboard lectures for you later on this week. So at very low frequencies, we have pulsar timing. At the very high frequencies, we have LIGO. LIGO is recently in the news with the merger of 2 very massive black holes that are, 100 solar masses, but our black holes are 1 billion solar masses. So, pulsar timing arrays are going to hold LIGO's drink for a little bit. All right. And then in the center, we have LISA. So LISA are in the millihertz band. And in the LISA band, you have the baby supermassive black holes. So those are like 10 to the 5 to 10 to the 6 solar masses, something like Sagittarius A star. It's big, but it's not, supermassive black hole that we're interested in big. These are 10 to the 8 to 10 to the 9. These are 10 to the 5 to 10 to the 6. And then LIGO is typically tens to maybe 100 if you're lucky. So they're complementary gravitational wave detectors. You could potentially have a gravitational wave that starts in the LISA band and that ends up in the LIGO band. You'll all have remembered the Susanna image from 2018, I think, where there's 10 years between the time to coalescence of something like GW 150914 and the LISA band into the LIGO band. But other than that, these detectors are all completely independent. Some of you might be wondering, well, if pulsar timing arrays can find gravitational waves that have strains of around 10 to the minus 15, then surely they would be screaming loud in LISA and blow away anything that you would find in LIGO, right? Like this is way above the detection curve. But you will have learned last week, I believe, about something called ISCO frequencies, the innermost stable circular orbit. And so for typical equal mass 10 to the 9 solar mass binary, the ISCO frequency is around 10 to the minus 6 hertz. So these black holes merge before you ever get into the LISA band. And so you're not going to have any kind of migration from pulsar timing arrays into LISA, even though in some instances it's possible to go from LISA to pulsar timing arrays. So they're complementary detectors. LIGO can't see pulsar timing array sources. And importantly, our sources in the pulsar timing array band are not transient. So you will have been used to seeing these kind of whoop chirps, right? In the LIGO band where you see a signal for a fraction of a second and everyone gets really excited about your 0.1 seconds of a signal. And that's great. But for pulsar timing arrays, the strains are so large that you can see these gravitational waves millions of years before they merge. And so our signal is all in spiral. So instead of it being the whoop, we have this kind of ohm, like at the end of a yoga class. So it's very low frequency monochromatic. It goes om, and it just stays om. And then not only is there one, but then the whole class gets together and everyone's chanting om at the same time and makes this gravitational wave background. Okay, so all of the detectors measure strain using light. For pulsar timing arrays, we look for changes in the arrival times in pulsar pulses. For LISA, you have a laser system set up that's very similar to LIGO, even though Neil will tell you that LISA is not LIGO in space. Like that's one of your famous taglines. And the last thing that I want to say is that this figure is from Mingarelli and Mingarelli 2018, where Mingarelli number 2 is Papa. And so if any of you have professors as parents and you decide to write papers with them, they're going to have a great time. But before you do this, come and talk to me. Okay, so let's get started on pulsar timing arrays. So galaxies have supermassive black holes at the centers. And when galaxies merge, their supermassive black holes should eventually merge. This animation is so old that it's cool again. So it's like this retro kind of thing that's really popular these days. So it's gone through a journey. So these supermassive black holes are around 10 to the 9 solar masses, and they're separated by a milliparsec, which is about the size of our solar system. It's the distance from the sun to Pluto. And these gravitational waves are something like a nanohertz. 1 nanohertz is an orbital period of about 30 years. Some of you are not an orbital period old of one of these pulsar timing arrays, gravitational wave periods. So when these gravitational waves are emitted in all directions, some of them make their way to the Earth, where we're studying these millisecond pulsars. So the pulsar pulses are so regular that any deviation in their arrival times could signal the presence of gravitational waves. And so if the signal were coming from the sky and into the floor from one of these supermassive black hole binaries, the back of the room and the front of the room would squash together and then stretch out, and then would be contracted and squashed again, right? So these gravitational waves that we're looking for have strains of something like 10 to the minus 15. In terms of timing, that's something like a timing difference over 10 years is like 300 nanoseconds, right? So your pulsars have to be extremely stable clocks in order to find a 300 nanosecond timing difference over a decade. If you want to think of change in distance over distance because you're a LIGON, you've been trained by LIGO, that is the size of a virus divided by the diameter of the Earth. So these are very, very small gravitational waves, but they're still 6 orders of magnitude larger in amplitude than anything that LIGO can find. And so how do we find these gravitational waves? Well, we time these millisecond pulsars using radio telescopes all over the Earth. So here in North America, we have the Green Bank telescope for now. Arecibo is gone. We have the VLA and we have CHIME in Canada. And in Europe, we have these 5 telescopes. Our favorite one is the Sardinia radio telescope because they host meetings there. And that makes for some very nice holidays. And so does Parkes. I think most of my students have been to Australia now for International Pulsar Timing Array meetings. Then we have the Indian Pulsar Timing Array, which has GMRT. And new to the party is MeerKAT, so the MeerKAT Pulsar Timing Array. They're going to be particularly important in the future because they have exquisite timing precision. And so there you can get really small residuals, which is what's going to be important for finding the individual supermassive black hole binaries. And then we have the Chinese Pulsar Timing Array. They have FAST. And I've heard informally that there's plans to build more telescopes like FAST, or maybe in the end like GPT. Importantly, there's no single point of failure for pulsar timing arrays. If you have a radio telescope and you can time pulsars, you can find gravitational waves. And so we have this huge collection of radio telescopes. The International Pulsar Timing Array is a global effort to combine all of these data in order to look for gravitational waves. But how do we actually do it? I've given you a lot of hand-wavy stories, and you've had a few chuckles, but how do we actually look for gravitational waves in these pulsar timing arrays? Well, here's an example of some pulsar residuals. And the residual is the expected minus the actual arrival time of the pulsar. So the residual is where your gravitational wave signal will live. So here you can see the axis goes from minus 0.6 to 0.6, residuals in units of 10 to the minus 6 seconds. And 0 is the black dashed line. You have different colors that indicate different radio frequencies that the pulsars were observed at different telescopes. And so not all of these are created equal. In 2012, there was a hardware upgrade at both telescopes, and you can see that the residuals are now much closer to the 0 residual line. You can also see here that there's no intrinsic structure in the residuals, right? They look like they're white residuals. This is really important because the gravitational wave background signal that we're looking for is a red noise. And that means that it increases as a function of time. And so if your pulsar intrinsically has its own red noise, it's really easy to confuse that noise with the gravitational wave background. And so when you're trying to look for your gravitational wave signal, you could mistake some of the pulsar noise for a gravitational wave background, or even worse, you could think that the gravitational wave background is pulsar noise. And in fact, that's a story for another day, but that happened. And so what you see here is the actual data that we use. Now, we use the data from this pulsar, which is called J1713 plus 0747. And we call this a pulsar phone number. And the name of the pulsar tells you where it is on the sky. The first part is right ascension, and the second part is declination. So there's about 200 known millisecond pulsars, and there are thousands more that are detectable. So this is not an experiment that's going to dry up and not have any more pulsars as detectors that are available. We're going to find potentially thousands more of these millisecond pulsars. So how do we find the gravitational wave signal? Now we know that the gravitational waves perturb the metric, right? It changes the proper distance between the Earth and the pulsar. Your pulsar signals get advanced or delayed, and you can find that in the residual. Residuals look white unless there's a red noise signal in it. That's bad because that can look like the gravitational wave background. So what we do with these residuals is that we cross-correlate them. We cross-correlate all of these residuals between, say, pulsar A and pulsar B, because the noise in each pulsar is independent, right? But each pulsar is bathed in this gravitational wave background. And so each pulsar will have some sort of imprint of the stochastic or the random gravitational wave background in it. And that signal should be the only signal that's correlated between the pulsars because they each have different noise. So the more pulsars you have, the more cross-correlated pairs you have, the higher the signal is and the less the noise is. So what we do is that we take one of these residuals and we cross-correlate it, not only with itself, but with a whole spectrum of millisecond pulsars. So here we have the NANOGrav 5-year data set, and then we had the 9-year data set, and we had the 11-year data set, the 12-year data set, and the 15-year data set. And if you now imagine, I wish I had an animation that did this, but what you do is that you take each one of these points and you cross-correlate it with itself and with all of the other points. So imagine doing this huge cross-multiplication of all of these terms. You take this residual and you multiply with itself, and then this one, and then this one, and then this one, and then you start over again. And you loop in your array and you cross-multiply all of these millisecond pulsars. So theoretically, when you do that, two things pop out. One is this characteristic strain, where there's a really nice straightforward formula derived by Sterl Finney in 2001 about how the characteristic strain relates to your binary population, and we'll derive that together. And the second term is this angular correlation function, which is like a 2-point correlation function. This is only a function of the geometry of the pulsars, and if you're lucky, it's a function of frequency. And if I have time, I'll try to get into that for you. But typically the frequency doesn't matter unless you're at very, very low frequencies and your pulsars are riding the same gravitational wave. Okay, so these are the two terms that pop out when you do the cross correlation. And that's why the next 2 lectures that I'll give are really focused on those 2 terms, because that's the foundation, that's the backbone of pulsar timing arrays, right? Is your angular correlation function and this characteristic strain. Those are the 2 things that you need to measure in order to know that you have a gravitational wave background. Okay, so this is the NANOGrav 15-year data set. There are 68 millisecond pulsars. You can see here that each one of these different colors corresponds to a different telescope that's observing at a different frequency. So AO is the Arecibo Observatory, GBT is the Green Bank telescope, VLA is the Very Large Array. I hope you're impressed, because I'm a theorist and this is not obvious, right? This is because I've been paying attention at telecons. All right, the timing baselines that we have are anywhere between 3 years and 15 years. And we've also been trying to automate timing with a pipeline, called PINT. And so, right now we have 68 millisecond pulsars, but what happens with the square kilometer array or with NGVLA with many more pulsar residuals, or with DSA 2000? These are all new telescopes that are going to have thousands more residuals, maybe tens of thousands more. So we can't keep doing this by hand every single time. All right. So what are we looking for? We're looking for a gravitational wave background. So I just told you that what you do is that you take all of these pulsar residuals and you cross-correlate them, and the only signal that should pop up when you cross-correlate all these residuals is the gravitational wave background. But where does that come from? Well, we believe that the primary source of the gravitational wave background is this incoherent superposition of gravitational waves from the cosmic population of supermassive black hole binaries. So these are very slow, in-spiraling sources. They typically don't have any frequency evolution over any observed window that you can measure, right? So over 10 years, your typical source is going to have an f dot of 0. And this is, again, completely different from what you would have seen with LIGO, where the source is evolving quickly in your band. In fact, it evolves so quickly, you can probably miss it because it's so transient. It stays in your band for 0.1 seconds. Our sources don't even change their frequency over the tens of years of observation that you have of the pulsar. So this is typically a monochromatic signal. So the primary source, we believe, are these supermassive black hole binaries. And at the very lowest frequencies, there can be hundreds of thousands of them that are in spiraling at the same time. And so it's not that we believe that every single galaxy has a supermassive black hole binary in it, and that's why there's so many of them. It's that these mergers take so long that by the time that you have an in-spiraling source, there's another merger that happens in another galaxy, and it's starting to in-spiral, right? So these can take tens of millions of years, and the incoherent superposition of all of these signals creates a stochastic or random gravitational wave background. Now, there's other gravitational wave background sources. It doesn't have to be astrophysical. In fact, the answer could be that, A total squared is some A1 astrophysical squared plus A2 cosmological squared, plus something, who knows, cosmic strings, domain walls. My student Chinyuan is looking at new physics, topological defects, lots of really interesting things that can create gravitational wave signals in the nanohertz band. The important part is that the detector itself doesn't change, right? Anything that creates nanohertz gravitational waves is going to induce this Hellings and Downs curve that I'll tell you about, that gamma AB. It's an angular correlation function, and it'll have some amplitude, which we interpret here astrophysically, but that interpretation of the amplitude can also be projected into completely different kinds of physics. The things that we actually measure are these two things, the characteristic strain and the angular correlation function. Here. Okay, so let's get started with the Hellings and Downs curve. What does it look like? So the Hellings and Downs curve is this correlation function. So if you have pulsars that are separated by a very small angle, their correlation is going to be a factor of +0.5. So it's not 1, because when you correlate the pulsar with itself, it doubles the correlation factor. So it's normalized such that for the autocorrelation term, you get 1. For everything else, it can be at most a factor of 0.5. If your pulsars are separated by 180 degrees on the sky, then they're at a value of 0.25, or half of whatever you have at the 0 plus epsilon value. This one is just a little bit higher at something like 175. And then you can have correlations that are close to 0, and you can have negative correlations. So in the limit of having an infinite number of pulsar pairs, you get this line that pops out, which is called the Hellings and Downs curve. So a positive correlation means that your residuals are bobbing together. They're correlated positively, right? They're bobbing up and down together like this in this gravitational wave C. If they're negatively correlated, it just means that one arrives early and one arrives late, and they're anti-correlated. That's all it means. So instead of doing the LIGO dance, which Bruce may or may not have done for you, right, where your interferometer goes like this, we go like this, right? Negative correlations and then positive correlations. So we're releasing an album together at the end of the month, right, Bruce? And I'll do the om, and you can do the whoop. Okay, so this is what your correlation function looks like. And there's a few interesting things about it. Firstly, it doesn't go back up to exactly where it started, right? So it's not exactly a quadrupole. And in fact, instead of doing the typical data analysis on the NANOGrav 15-year data to look for evidence of this, you can do a harmonic analysis and then try to fit all of these different Legendre polynomials and prove to yourself that, in fact, you have a certain contribution from a quadrupole, but then you also have all of these different harmonics that add to it. I'm not going to go into that today, but if you want, there's a paper led by Jonathan Ney, who's a student working with Kim Boddy at UT Austin, who did a really nice job on this. The minimum is not exactly at 90 degrees or pi over 2. It's kind of shifted. It's at something like 78 degrees. And again, it's not a pure quadrupole. That's why. Okay, so what else is there? How do we get this Hellings and Downs curve? So what we do is that we take the response to a pulsar pair from a single incoming gravitational wave, and we integrate it over the whole sky. And I had this undergraduate who was working with me over the summer make a little animation of what this looks like. So this blue curve is the Hellings and Downs curve. And this is what you get in the limit of having an infinite number of supermassive black hole binaries. But if you start with just a few, I'm going to start this animation in a second. This is just an example of what this is going to look like. You don't get something that looks like the Hellings and Downs curve right away. You have to have multiple sources that are average to give you the Hellings and Downs curve. We find that after about 15 sources, you do get the Hellings and Downs curve. You also don't exactly get it when you do this thing discretely. And this may or may not be due to something like cosmic variance. And it gets worse with the more pulsars that you have, right? Because now your error bars get really, really small. So at first you're okay, but in fact, you never perfectly get the Hellings and Downs curve if you have a discrete number of sources, but it doesn't take long to get there. So this is just to show you that, for something like 20 sources, now that you've already seen how this goes, you already get something that looks Hellings and Downsy. And so this is a kind of thing for you to keep in the back of your mind, right? That even though now we think we found this characteristic strain and we found the Hellings and Downs curve, and that's why we're talking about it today, we might actually be dominated by something like 15 or 20 really loud sources, and the rest of the background might come from something else, right? So there's only certain ways that we can tell the difference between these two things, like looking at the strain spectrum. Yeah.
Do you assume that all pulses have the same amplitude, or do you give them like geometric?
This is just for the geometric component, not for the amplitude. Yeah, so if we had an amplitude, then I would have an a squared gamma AB that pre-multiplies it, and then this would be like times 10 to the minus 29 or something like that. So this is just for the geometric part of the correlation function. So when you have your two antenna beam patterns, your F plus and F crosses that I'll derive for you in the next lecture, these are only a function of where your pulsar is on the sky with respect to your gravitational wave source. Okay. All right. So next is why are we so excited about the gravitational wave background? Well, I've been excited for a very long time, but now my enthusiasm is shared by more people. So this is the expected correlation curve that you get, and these are the measurements that we made with NANOGrav. For those of you who are trying to do chi by eye, this is not the right way to think about it. This is a little figure that we put together to just show you, if we binned these results, this is what their error bars would be. In reality, we have 2,211 binned pulsar pairs. And so you have to find some way of presenting the data that looks reasonable. And so here, we have something like 20 bins. If there were no gravitational wave background, there would be no correlation. But there is definitely a signal here, and the significance is something between 3 and 4 sigma, depending on the different tests that you do. So we're excited that there's now evidence for the gravitational wave background. Of course, we can't say detection until we hit 5 sigma, but it's difficult to understand what else it could be. But there still might be other things happening that we have to clean up in the data, like pulsar noise. For the Bayesians who are not interested in p-values, the Bayes factor of having this gravitational wave background versus just some common red noise signal is 900 to 1. So we're pretty sure that what we find has these Hellings and Downs correlations, and that it's a gravitational wave background. Okay. So now, part 2. That was half an hour. That's good. All right, so the characteristic strain. I told you a little bit about this earlier, and we're going to derive exactly where this formula comes from in the next lecture. But the characteristic strain is basically just the sum of all of the strains from a cosmic population of supermassive black hole binaries at a given frequency. You can do lots of fun things and multiply by 1 in lots of beautiful and wonderful ways to rewrite your equation to get something that looks astrophysical. And in fact, that was a really nice contribution from Alberto Susanna, who figured out how to write this in a way that would enable you to directly probe things like galaxy merger rates and black hole chirp masses, even though the mass dependence came out in Finney 2001. So basically what you do here is that you say, I'm going to take dE by d log f of all of the sources at a particular frequency. I add them in quadrature. This is my characteristic strain. I, at that particular frequency, integrate over mass, or here it's chirp mass, and I integrate over redshift, and out comes some sort of amplitude of the gravitational wave background at a specific frequency. If I assume that the binaries are circular, then I can decouple the frequency dependence and bring it out into the front, and you can see that the strain scales like f to the minus 2/3. And that's a really nice scaling laws. If you haven't figured it out by now yet, astronomers love scaling laws. Everything is a power law, right? And so if you can write this down as a power law, immediately you have the psychological factor. People want to believe you. So you can write this characteristic strain as some amplitude times f to the minus 2/3. And this amplitude is the value of this double integral, which means that when you find the gravitational wave background, you can take this amplitude and decompose it into things like galaxy-galaxy merger rates and the chirp mass, and also the redshift that encloses the background, right? That's going to be the effective bounds of the integration. So all of this information is encoded in this amplitude of the background. And we report this background typically at a reference frequency of 1 over a year. And that's just so that when we're comparing different amplitude measurements from different experiments, we're doing as much as possible an apples to apples comparison. For the cosmologists in the room, maybe you're more interested in omega GW, that scales like the characteristic strain squared. And just to remind you of how all these things work together, you take your pulsars, you cross-correlate them, out pops two things. The Hellings and Downs curve, they have to have that characteristic swoopy shape, and this characteristic strain, which is the amplitude of the swoopy shape. All right, so if we look at something like a realization of the gravitational wave background as a function of frequency and looking at a discrete source population, this is what your spectrum looks like. So here you have gravitational wave frequency, and here you have characteristic strain. This is the f to the minus 2/3 power law that we will derive together that you just saw a sketch of in the last slide. And this is your discrete model. And so your discrete model can get this f to the minus 2/3 at any frequency, because if you do this averaged population, you can have a fraction of a source that contributes at a specific frequency. If you have a discrete population, you don't have that fractional source that you can add, and you get this deviation from the f to the minus 2/3 power law. And so this is great in a sense. It shows you that at very low frequencies, like at 2 nanohertz, which is 1/15 years, you have something like 10 to the 6 supermassive black hole binaries. So in terms of astrophysics, this is where you can get a really great signal to describe the source population. If you're interested in individual supermassive black hole binaries, you're probably better off looking at sources somewhere between 20 and 50 nanohertz, because here the stochasticity of the background is breaking down. You don't have so many sources that are contributing to the background. And so the background, which is now a source of noise, is really damped down by the fact that you're having fewer sources there. If you want to get a really kind of gut punch feeling about how few sources there are, if you go from 2 nanohertz to 20 nanohertz, at 20 nanohertz, you have something like 10 to the 3 binaries. And so you have a 3 order of magnitude difference in binaries between 2 and 20 nanohertz. Yeah.
So if you have 10 to the 9 plus 10 to the 9, that's allowed as 1,000 10 to the 6 plus 10 to the 6. Now, it could be possible that most of the energy comes from the high masses, but there is going to be some energy from the 10 to the 7 plus 10 to the 7.
So the majority, in fact, I think you're maybe even anticipating my next slide. You are. So the next slide shows how you can decompose the amplitude of the background into binary black hole mass populations. And so we'll get to that next. So this is just showing you if I have the entire source population, how does this work? So that includes something like 10 to the 8 solar mass binaries, even a little bit lower. The lower ones, I'll spoil my next slide for you, don't really contribute very much, even though there's more of them. These are typically, so this particular realization is done with binaries that go from 10 to the 7 to 10 to the 10 or 10 to the 10.5 solar masses. But what I'll just show you now, what I'll find here is that the minimum black hole mass contributing to the background is about 10 to the 8 solar masses. And so you can have as many 10 to the 7 binaries as you want. The amplitude that they contribute to the background really doesn't compare to what you get from the 10 to the 8 solar mass binaries. But you're right, if you're thinking about some black hole mass function, there's way more 10 to the 7, 10 to the 8 binaries than there are 10 to the 9 or 10 to the 10. And so the population really is dominated by these 10 to the 8 solar mass binaries. You're totally right to think that. But the individual detectable ones will probably be the heavier ones right now. But so to answer for everyone else, this question in a bit more generality, I promised you that if I measured the amplitude of the background that I could decompose it into the binary population statistics. And so that's what we do here. So this is an extension of a paper written by my student Andrew Casey Clyde and Jenny Green, who's giving the talk after this one, where we take the NANOGrav gravitational wave background amplitude and then decompose it into the primary black hole mass, so black hole mass 1. And we find that this is really dominated by the 10 to the 8 solar mass black holes. We can also constrain the number density of black hole binaries to be something like 1.1 times 10 to the minus 5 supermassive black hole binaries per megaparsec cubed. And we can also constrain the volume of the gravitational wave background to be within something like redshift 2.5. And so now that we have this amplitude of the background, we can decompose it into these population statistics. And the better we measure the background, the better we can measure this underlying supermassive black hole binary population. And so there's some interesting things that you can measure, not just from the general population statistics, but by looking at the strain spectrum of the gravitational wave background. So here you have your f to the minus 2/3 power law, which is vanilla as it gets. It assumes everything is wonderful in the world of black hole binaries. None of them stall. They all merge in a Hubble time. Everything is wonderful. They're all gravitational wave driven and they're circular. It's the bedtime story you tell your students about the gravitational wave background. In reality, there's all of these boogeymen, right? You have environmental coupling, so your binaries could be eccentric, right? They probably are eccentric. If you have all of these supermassive black hole binaries that are merging over some cosmic history, it's probably very unrealistic to believe that they're all just going to find each other and start, singing Kumbaya, holding hands in a nice circular orbit. Untrue, right? But how does that affect things? It makes the strain spectrum turn over. So does stellar hardening, which is how you solve the final parsec problem. So if you have your two black holes that sink to the center of this newly formed galaxy and they start in-spiraling, they can get to within about a parsec of each other, but then they kind of stall out there if there's nothing external acting on them. It takes many Hubble times for them to merge under gravitational radiation only. What happens, or how you can solve this, is if you have stars that are crossing the binary's orbit, and the stars will get slingshot out, and each time you have one star that crosses and gets slingshot out, it carries away energy and angular momentum from your system, and that makes the binary shrink just a little bit. So if you have a mass in stars that's equivalent to the mass of one of the black holes, then you have enough energy loss to get the black holes to within a milliparsec, where gravitational wave emission is the most efficient thing to make them merge. Now, it's a blessing and a curse, again, because at these very low frequencies or wide binary separations, all of these mechanisms are much more efficient at making your black holes merge than gravitational waves, right? These stars crossing your binary that's maybe or maybe not stalled are more efficient. If you have gas that's being accreted onto the binaries and it's inducing a negative torque, then your binaries will, again, merge more quickly. And if they're eccentric, they're emitting all of this additional gravitational radiation at the high order harmonics that's also making them merge more quickly. All of these things deplete what your gravitational wave signal is at these very low energies until a certain point. Once you get to about 10 nanohertz, only gravitational waves are going to make your binaries merge. But this makes an interesting signal that you can look for. So in astronomy, we call this a turnover, which is what it says on the tin. The spectrum turns over. So if there's nothing happening to your black holes other than they're circular and they're in-spiraling slowly under only gravitational wave radiation, you have f to the minus 2/3. But if there's other things that are happening, right, this kind of astrophysics that's affecting the binary population, your strain spectrum turns over. This is one of the ways that we can look for an astrophysical influence in the spectrum of the gravitational wave background. Now, the other thing that people are really excited about these days is the amplitude of the background, right? What does the amplitude tell us? Well, we know it tells us about the black hole masses in specific, but it can also tell us about merger timescales, black hole host relations, which again give you black hole masses, the pair fraction, and how all this evolves as a function of redshift. So while environmental couplings make your strain spectrum turn over, black hole masses, remember the characteristic strain, squared scales like the black hole strip mass to the 5/3. So it's a really powerful way to shift your amplitude up and down. And that's something that Matthias and Gabby are looking at in more detail to understand if any of these things are reasonable or not, right? Is the amplitude reasonable? And how is it related to these observables, in particular, these black hole host galaxy scaling relations? Okay, so amplitude shifts up and down with black hole masses, basically. And then the strain spectrum, which turns over or not, is an indication of any kind of environmental coupling effects. Yes?
So, what's the rate of the large that they don't expect to make black hole binary to be in the band of the
What's the rate of stellar hardening?
Yeah. How many stars stellar interaction?
Well, so this gets into, it's a complicated answer. So what happens is that you can have something called the loss cone, right? So your stars can interact once with your binary and be ejected. The important thing is to have a total mass in that volume of stars around your black holes that's equivalent to the mass of one of the black holes that shifts away enough energy to make them merge. And so that distribution and the number of interactions depends on that quantity. But there's some people who argue that something called this loss cone can be depleted, which means that your black hole, your stars only interact once with your binary, and then they're sent away. Maybe they create hypervelocity stars, but they don't get recycled and they don't come back. And so this could also create another stalling mechanism for the black holes. So it's, I don't know, there's a distribution in terms of, you know, the mass and the interaction right there to answer your question. Okay. All right. So this brings us to the second NANOGrav 15-year result. So the first one I showed you was the Hellings and Downs curve, and you were all shocked and amazed by what you saw. It's okay to laugh. It's early. All right. The second thing that I think is really interesting is when you look at the strain spectrum from the gravitational wave background. So now you know how to interpret this. If you look at this panel here on the right, characteristic strain versus frequency. This is exactly what I showed you here. Characteristic strain versus frequency. This is our cartoon universe where everything is wonderful. This is reality. And we're like, what's this? What's happening? So if you have this f to the minus 2/3 power law, right, you should have something that just scales as a function of frequency to the minus 2/3. No problem. Alpha is 2/3. Supermassive black holes generate your background. But if you look at the best fit supermassive black hole binary model, it's this blue line. What is that doing? It sort of looks like it's turning over, right? But if you then plug in some sort of Bayesian model to say, what model do I prefer? Do I prefer a turnover model, or do I prefer this flat model? You know, it's only a Bayes factor of a few in favor of having something turn over. So really, we need more data to understand what exactly is happening here at 2 nanohertz. But then there's this question, right? If this is supposed to be f to the minus 2/3, then this is kind of, well, what is it, right? What's happening? You can also look at it in terms of the residuals. And to get to residuals, what you do is that you take the cross power spectral density, SAB, you divide it by time, and you take the square root of it. So it's an amplitude spectral density, closer to what they do in LISA. And this scales like f to the minus 13/3. And so here, if you reprocess the data and look at it here, it still looks kind of terrible, right? Everything else looks pretty much okay. So what's going on here? Why is there a bump here? So we looked into this and then thought, well, maybe this is just something funny happening in the NANOGrav 15-year data. But let's look at the NANOGrav 12.5-year data. Maybe we just didn't notice it before. Has it always been there? And so we reprocessed the 12.5-year data to be, and the 15-year data to have the same frequency bins. Because normally the binning goes like 1 over time. So if you have 2 different time scales, then you need to agree on one time scale to use and then reprocess the data so that it has the same bins. So here we have this discrete model, and you know, things kind of move around between the 15-year data, which is blue, and the 12.5-year data, which is pink, except for at 16 nanohertz. Right? This looks the same. And so then that was like, well, what could it be? Whoa. And thank you for your attention. That was like, no, we already published the results. I'm not leaking anything, I promise. Okay, let's go back. So many animations. So what we were trying to figure out is what's causing this excursion from the power law? And do we really expect it to be a power law at all? Right? Why are we obsessed with this idea of having a power law? The power law comes from an ensemble average. And in reality, you're going to have one realization of the universe, which is itself discrete and not some sort of power law. And so what's happening? So at 16 nanohertz, you have this bump, right? It jumps up, and this is something like a 2 sigma deviation from your power law. And what we found is that if this is one extra supermassive black hole binary, then you would expect in your discrete model, that's enough to make this particular bin jump up. And in terms of the continuous wave limits, which we'll look at a little bit more now, the continuous wave limits tell you if I do an all-sky search and I look for some sort of sinusoidal signal instead of a stochastic one, what is the signal limit that I get? And that rules out this part of the parameter space. If I look at the power here, or the strain, versus the characteristic strain, and I take the difference between the two, and I have some sort of excess power between them, I can decompose this into an additional luminosity, distance, and mass, and you would be able to describe that difference in strain by continuous wave with these source properties. So it would be at a frequency of 16 nanohertz. It could be at a gigaparsec and be very massive, or it could be very nearby and have a lower mass. It's one possible interpretation. Another one is that it's just noise, right? It would be about 10 nanoseconds of white noise residuals that's unmodeled that could potentially create something like this. But it gets you thinking about, why is it that we're obsessed with measuring gamma equals 13/3 or f to the minus 2/3, however you want to talk about it? Because in reality, this is what we measure. This is one realization of the universe, and we live in one realization of the universe. So why on earth are we always banging our heads against the walls, being so scared that we're not measuring gamma equals 13/3, when in reality, that's your average over multiple realizations of the universe, and we live in one. So the one universe that we live in is going to have some excursions. It's going to have some, underdensities and overdensities. It's going to be jagged looking like this. It's not going to be something smooth. And so this is the particular realization of the universe that corresponds to a strain spectrum that looks like the 15-year one. And we just have one more supermassive black hole binary than you would expect at that particular frequency that makes that excursion. So that's a possible interpretation of it. And it's an interesting thing to look at. And I know that Gabby and Matthias are also interested in the discreteness of the supermassive black hole binary population right now. Yeah.
Can you make those laws for separate but big enough at the sky? And like what will they do? Stereo of the sky?
So do you mean that would these induce any kind of measurable anisotropy in the gravitational wave? Well, so these do average over the whole sky, right? This doesn't give us any kind of angular component when we do this particular version of it. This source could be anywhere on the sky. I mean, the way that you're thinking about things is really good. You're thinking about where is the source on the sky? Maybe where is it relative to the pulsars? And where is there more power in one part of the sky than on the other part of the sky? Those are all really good, relevant questions. But for this kind of analysis, you don't have any kind of angular dependence or any kind of sky position dependence. You're averaging over the whole sky. Your source could be anywhere on the sky. This is all of the supermassive black hole binaries on the sky with the NANOGrav 68 pulsars responding to that background. Yeah. Kind of like a jackknife or leave one out analysis where you take different subgroups of pulsars. Yeah, definitely. So we in NANOGrav call that dropout analysis, but it's exactly what you're describing. And you look for if pulsars favor having a specific signal in them or not. I don't have that figure here, but that's something that we did. And that was also a really interesting analysis. I'd be happy to talk to you about it afterwards. So if you look at the Arzoumanian et al. 2023 paper, and you look at, it'll actually show you this exact analysis called a dropout analysis. That's what it's called here. Yeah, but that's a great idea, and we did it, and I'm glad we did. But if we hadn't, this would have been a really fun paper to write. Okay, and so now comes the detection, maybe, of individual supermassive black hole binaries, right? So this discreteness analysis is one step that's kind of in between looking at the strain spectrum and then saying, well, there's a bump in the spectrum, and is that an individual supermassive black hole binary? Well, then how would we know? And this is really where we're at right now, is how do we know what's real and what's not real and what's signal and what's noise when we're in this very, intermediate regime where we're transitioning from having detected, imagine the monopole of the CMB, to trying to look for anisotropies, right? We just found the monopole, and now we're kind of getting into being able to characterize it, but things are really degenerate. So how can we help ourselves along, given the fact that we know that massive black holes are in massive galaxies, so we should probably look there to find the inspiraling, very massive black hole binaries. We're also aided by these large hydrodynamical simulations that were performed by Ferris et al., who was working with Paul Duffel. So this is Andrew McFadgen's group at NYU and also Zoltan Hyman. And what they found is that there's this lump that forms in the accretion disk around the supermassive black hole binaries, and that period roughly traces the period of the binary. It depends on a few things like the mass ratio of the binary. It also depends on if the binary is eccentric or not. But for today's class, we'll just say that it roughly traces the binary's orbital period. And so how does that help us? Well, in Arzumanian et al. 2021, or actually it was the 2020 paper, Caitlin Witt, who is the corresponding author, showed that if you take your Bayesian analysis and instead of searching over all of your source parameters, if you take a certain spot on the sky, you fix your RA and your DEC, these are delta function priors. And if you also know what the gravitational wave frequency is, you can improve your strain upper limits by an order of magnitude. But that was just done for one source called 3C66b, which is a relatively nearby supermassive black hole binary candidate. If you only know the sky location, then you get an improvement of a factor of 2. But if you know sky and frequency information, you get an order of magnitude improvement. So some students in NANOGrav, most recently Polina Petrov, showed that even in your best possible scenario universe, you can't resolve a single patch on the sky to better than about 29 square degrees, where there's a supermassive black hole binary. And a lot of people have thought about this, including Neil and Neil's student Bense Becci. So what do we do? How do we do this? Well, we can look for periodic light curves that we actually find in some AGN that may or may not trace these supermassive black hole binaries. On this side of the sky, or the side of my slide, you'll see the NANOGrav 11-year data. These white dots are the pulsars, and these guys are the most interesting Catalina real-time transient survey active galactic nuclei that had these periodic light curves that may or may not actually trace supermassive black hole binary activity. And so some of them are aligned with pulsars, which makes them extremely interesting. You get a boost if your pulsars are very close to the gravitational wave position on the sky. And then we showed that if these guys are real, and this one here is 3C66b, that we'll eventually be able to detect them. So we started populating the sky, not only with the NANOGrav pulsars, but then estimating what IPTA 2025 would look like. We don't actually have a real IPTA 2025 yet. We have a preliminary internal data set now for IPTA, but I can't share that with you. And then we looked at what would happen with SKA phase 1 and SKA phase 2. What's important here is to look at these strain bars on the sky. So this is the minimum detectable strain at 12 nanohertz. Here you see with the NANOGrav data, you have this really big cold spot, and the rest of the sky is hot. And this varies by an order of magnitude. And then with IPTA, you're starting to isotropize your pulsar timing array, right? The cold spot is not as cold as it was. Now it's only a factor of 2. And here with SK phase 1, it's almost negligible where your source is on the sky. You're going to have a very similar detectability. And with SK phase 2, it's something between 5 and 5 times 10 to the minus 17. So the important takeaway here is that as you add more pulsars to your pulsar timing array, we're not so sensitive to where on the sky your signal is. It really isotropizes the response of your PTA, and we don't have to be so worried about having a bad place on the sky and a good place on the sky, which is what we do right now. Bruce, I see you stewing in a question.
I'm confused about something here. So
Tell me.
if I understand right, the color scale is different.
That's right. Yeah, it's the minimal detectable
I
strain.
just can't read the difference between the coldest and the hottest.
Yeah, so
Can you
this
tell me
is
what that is?
absolutely. So up here, it's 2.5 times 10 to the minus 15 to 1 times 10 to the minus 14. That's
Factor
big.
of 4. Factor of 4.
Sure. And then here you have 4 times 10 to the minus 16 to 6 times 10 to the minus 16.
So factor of 1.5.
And then here is 10 to the minus 16 to 1.3 times 10 to the minus 16.
So the top left one goes over a factor of 4, whereas the bottom left one goes over a factor of 30%.
That's right. And then it gets smaller and smaller and smaller. Yeah. All right. So in this pilot study that I carried out back in 2017, looking at the local population, it appeared that something like 2 supermassive black hole binaries would have 2 sigma level evidence in our eventual data by 2030. And we have yet to see anything like that. But it begs the question, what's going on with the targeted searches now? So the first targeted search paper was in 2020. And that was done with a galaxy called 3C66b. And that is this purple dot here. And so what are we doing now with targeted searches? So in the NANOGrav 12.5-year data, which came out in 2023, we improved our strain upper limits, but still weren't in any kind of astrophysically relevant regime. But in the NANOGrav 15-year data, which is this targeted search paper that I'm writing with my students, you saw Chin-Yuan and Bjorn here. I'll share some of the results now in terms of the improvements that we've made with these targeted searches. And so we're now doing 32% better than we were with regards to the 12.5-year data. And this is the first time we've actually measured an improvement that now challenges an astrophysical interpretation of a supermassive black hole binary. So we internally, I don't think anyone believes that this galaxy hosts a supermassive black hole binary. But now, we're really starting to show that it's impossible for this particular galaxy to host a binary. And whatever's causing, this offset nucleus in the particular galaxy wasn't due to a merger. It's probably just something else. So it's for the first time we're probing this mass. It's really interesting. And we're cutting into this range. Bjorn Larson made this figure, but it begs the question, this is just one source. That was our first source that we've been looking at for a while. What about the other ones? So I had this really good undergrad, Forrest Hutchison, and I'd said, why don't you look at 10 of these sources from CRTS? And then over the holidays, he was like, I saw that no one was using your private partition, so I just decided to do the rest of the galaxies in this whole catalog. And so now we have 113 upper limits. And if you've ever done this, kudos. This was a huge undertaking. And we now have gone from this pilot study right here for 3C66b to targeted limits on all of the CRTS candidates. 2 of them are really interesting, so I'm not talking about them today. We call them Rohan and Gondor. Some of you have read Lord of the Rings or have seen the movies. This was another undergrad that I worked with called Rohan, who did the search and found Rohan's binary. And then when we found a second one, we had no choice but to call it Gondor. So you can see there's some interesting things, though, even from this very general overview. Like some of the targeted upper limits are worse than the all-sky ones. And we're still trying to understand why that's happening. Is it because there's bad parts of the sky where the binaries are, so the all-sky upper limits, when you average them, gives you a better value than if you just targeted that one part of the sky? Is it that this is a bad frequency? Are there dead zones in our frequency space that we don't quite understand? They're things that we're still working on. But overall, we found that you have a factor of 3 in improvement using these targeted searches over the all-sky upper limits. Where do these improvements happen? Well, some of them happen in frequency space. So at around 15 nanohertz, here at like 14 nanohertz, we have a few targets that were improved by a factor of 15. But overall, there's no clear trend as to which frequencies are the best frequencies that have been improved. However, as a function of redshift, you can see that most of the big improvements happen within a redshift of a half. So it seems like the targeted searches are most effective for nearby sources that improve things. This is a factor of 14.7 for that particular galaxy. But really, everything gets improved by around a factor of 3 to 4. And as a function of sky position, it's also not clear if there's a particular sweet spot on the sky. So some of the sources that were improved the most are here in yellow. All the other ones are blues. So it seems like there's not a particular sky location that we prefer that we have improved targeted upper limits in. Okay, so say that we do find something. What if we did find some sort of low Bayes factor continuous wave signal using these targeted searches? And remember, with the targeted searches, we fix the sky location, we fix the luminosity distance, and we fix the frequency. So how do we know that what we found is actually what we think that we found? What are some of the tests that we can do? What's that? The frequency comes from the periodic light curves from the CRTS catalog. Yeah. So one of the tests you can do is to say, are these still periodic? Right? 90% now of the CRTS sources from 2015 are no longer periodic. So only a few of them are still periodic. So are some of these just red noise? Did they only look periodic over the time that we actually measured their periodicity and now they're no longer periodic? Are there other electromagnetic counterparts? Jenny Green is going to talk about this in the next talk. How do we know from an electromagnetic perspective that there's 2 black holes? Can we do any self-consistent tests of the gravitational wave background? What if all of the CRTS sources are really supermassive black hole binaries? You can derive a contradiction in the amplitude of the background. So we know that only something like 5 or 8 of them can be real. And we can also look at population synthesis models. How many continuous wave sources should we have as a function of frequency to be consistent with the gravitational wave background? Furthermore, are any of these sources so loud that they should have induced a detectable level of anisotropy in the gravitational wave background? And do the sources prefer a coherent sinusoidal model, or does it prefer something that's just the gravitational wave background? We can do these coherence tests. And my friend in the back with the dropout analysis that he invented as a question with the white hat. I think you're on your phone. Yeah, it's okay. I was going to point at you with my laser pointer, then thought that might be rude or dangerous. We also did that kind of test for these supermassive black hole binaries to see if they preferred to have this continuous wave signal or not. And then we can look at excess noise, right? Is it pulsar noise that's making us think that the signal is real, or is it something else? Can you guys think of additional tests? How would you try to figure out if one of these black hole binaries is real? To be fair, like, we really tried hard to come up with this list. This is highly non-trivial to create. If you think about anything, please do let me know. All right, so that brings us into this detection of individual binaries to the anisotropy in the background. So there's 2 different kinds of anisotropies that we're sensitive to with pulsar timing arrays. We have the, we call it Poisson noise, cosmologists call it shot noise. It's just if you have a really loud source that blinds you to everything else, that'll induce anisotropies. At high frequencies, we think that this comes from individual binaries. And at low frequencies, now your single source is competing with the whole cosmic population of supermassive black hole binaries. So the probability that there's one that's louder than 1 million sources at the same frequency is low. It's not 0, but it's still low. And so at these very low frequencies, we then are sensitive to measuring something like the large scale structure of the universe. right? Because the supermassive black hole binaries are in galaxies. The galaxies trace the large scale structure. And so when you get rid of the shot noise on top of it, what you're left with is a nice map of the large scale structure. And so Emiko Gardner, who's sitting right here, raise your hand, made this really nice animation of anisotropy, going from the monopoles to dipoles to really bringing the gravitational wave background into focus, right? So right now, we just found the blob, and just ignore a kinematic dipole. And then you slowly get better and better and better, and we can bring the whole astrophysical population into focus. And so these individual sources will first induce some sort of anisotropy. What does that look like for pulsar timing arrays? So here, this is from a study that I led in 2017 that looked at astrophysical sources that are nearby. If you take this local population and then say, what does this look like in terms of an incoherent signal? If you take them all and add them together with a loud source, you get this one bright spot, this kind of shot noise that dominates everything. And if you take the angular power spectrum of the sky, you get this blue line. Those of you who have used HealPi or HealPix will know that this Gaussian tail here just comes from the smoothing of the map. It's not real, right? That if you don't have the smoothing, it's just a flat line across all these higher order multiple moments. But what if you're not so lucky to have something screaming loud nearby? What happens is that you have this kind of sky map, which looks much more like a, I don't know, cool CMB style map, but it's astrophysical. There, you get that the level of anisotropy is something like 20% of the monopole. And so you can have screaming loud sources. They're all going to be flat. You can have this kind of background shot noise at a level of 20% of the monopole. People are now really getting into studying the anisotropy in the background, and we've made a lot of progress in the last 12 years. Okay, but how do we find them? Well, we saw earlier that you have the Hellings and Downs curve. You can also decompose the background on a basis of spherical harmonics and look for these different angular correlation functions. They each kind of look like a piece of spaghetti, so I call them this is the spaghetto plot because there's just one. And then multiple, keeps getting worse and worse and worse. But what if you then relax your assumption that the Hellings and Downs curve or all of these spaghetti plots, these different angular correlation functions, come from tensor values? What if it's not just F plus and F cross, or these two polarizations? What if you have something beyond general relativity? And so there was this really nice paper from Mark Kemiankowski's group, which looked at different contributions to the gravitational wave background, looking first at the F plus and F cross, or the tensor polarizations, and then looking at the scalar tensor contribution. This is a breathing mode. So if your regular plus and crosses look like this, right? Your breathing mode goes like this, right? It's coming in and out, and your circle of test masses is breathing. We can also look for those, and those come in through this gamma AB. So gamma AB has all of these different angular correlation functions, which are just a function of the geometry of your pulsars. So you can have plus and cross, and you can have all sorts of weird deviations from general relativity that we would be sensitive to through pulsar timing arrays and cross-correlating all of these pulsars. Okay, and then the last thing I'll tell you about anisotropy is that at these very low frequencies, you can in fact trace the large scale structure. So on the left-hand side, this is a map that shows the large scale structure. Now, if you're a cosmologist, you'll say, of course, that's the large scale structure. But if you're an astrophysicist, you might say, like, that looks pretty random. I'm not sure that I believe that there's any structure in this. I asked the student to then just isotropize this. So this is what a truly random sky looks like. And then you can see the structure if you refer back to it, right? So this is just to guide your eye to say, there's definitely structure in this map here. And this is an isotropization of this side. So if you believe that your supermassive black hole binaries follow this large scale structure, and they definitely should, unless we're dominated by primordial black holes, which are not in galaxies, but that's another fun thing we can think about. You can eventually see that the black hole binaries that you detect will also follow this large scale structure. So we simulated galaxies out to redshift 2 using the NANOGrav 15-year data. We know that something like 1 to 3% of galaxies host supermassive black hole binaries. And then we recovered the signal. We removed the loud supermassive black hole binary systems. And we found this imprint of the large scale structure by doing a cross correlation search between the gravitational wave background and the galaxies. And we found that for future detectors with L greater than 40, we can make a 3 sigma detection of the large scale structure. And if we ever get to L equals 70, we can make a 5 sigma detection of the background. And the last thing that I'll tell you about in any kind of detail is noise. So pulsar noise is really, really important. And Bjorn has become the pulsar noise person in NANOGrav. You might have seen his poster. You showed your poster. Excellent. And these are custom noise models for 6 pulsars. So I'll walk you through this. If we look at this pulsar here, J1012 plus 5307, what you have here are these 3 contours and then this dark one here. So these are different NANOGrav noise models. And this is what you get for the gravitational wave background. This is where you expect the signal to be. This pulsar is so noisy that none of these contours are close to the gray one, right? This is a really high amplitude. It doesn't really matter what you do. You're never going to get down here to where the signal is, right? So what happens if you use these custom noise models is that you can get a lot closer to where the signal is. Or maybe you thought that you were close to the signal, but you really weren't. So if you look here, for example, in J1713 plus 0747, which is the first pulsar that I showed you at the beginning of this lecture, this is the gravitational wave background signal. And these are the previous noise models that we used before Bjorn's custom noise model. And they were sort of close to it, but you can see once you apply Bjorn's custom noise model, this ellipse is really big, right? And the fact that it's really big means that we previously underestimated how noisy this pulsar was. We thought it was really good, but in fact, it is not so good, right? Now you have these huge error contours. And if you believe, in fact, that the gravitational wave background scales like gamma to the 13/3 or 4.33, then you can see that now this noise model does cover the astrophysical background, or gamma is 4.33. So these noise models were somehow taking this intrinsically noisier than we thought pulsar and moving that noise somewhere else. Right, so there's this really weird noise mixing that happens. And Bjorn can tell you about chromatic noise versus achromatic noise. And he can tell you about how all of these things work. But in fact, this has been a huge problem that we've only really started to wrap our heads around. So some of you who've been following the literature for the past few years might have been surprised by the amplitude of the gravitational wave background that we found, right? When we published the evidence for the background, we said that the amplitude was 2.4 times 10 to the minus 15 at a reference frequency of 1 over a year. But those of you who are paying attention would be like, wait, didn't you already rule that out? Because I remember a previous limit that was like 1.1 and another one that was like 1.4. So how did you find something that you've already ruled out before? And that's because of all of this pulsar noise. So the pulsar noise, we thought that what we were seeing in the pulsars was noise, but it was the gravitational wave background signal. So we couldn't actually distinguish between the pulsar noise and the gravitational wave background, or we were doing it really badly. And so we kept seeing this red noise that was in all the pulsars and thinking this can't possibly be the gravitational wave background. The amplitude is too big. And so how do we get rid of this signal? And so we did everything we could to get rid of this signal and get rid of the signal until we actually ate away at the signal. And then we took a step back and we were like, wait, what are we actually doing here? What's happened? What's going on? And then we found that with these custom noise models, it was much easier to disentangle the red noise in the pulsar from the gravitational wave background signal. So you can see here, even if you're not an expert, that the gray things are what we what we think the gravitational wave background is without custom noise models. And the blue things are now what we get with Bjorn's custom noise models. So in some ways, like in this particular pulsar, you know, it's extremely noisy. You don't even have a closed contour. Whereas before you thought you were doing great, right? So there's a lot of weird stuff that happens that we're starting to now model, including things like the solar wind, right? So when your pulsar pulses pass really close to the sun, there's extra electrons that are close to the sun. And we have this thing called dispersion measure in the pulsars. And so you think that there's some sort of integrated electron column density between you and your pulsar. And you can figure out sort of what this is with different maps of electron densities. It depends on your map of the spiral arms in the Milky Way. But really what happens is that you think you know what this is, and then you make a measurement, and you try to figure out how dispersed your pulsar signal is. But if you're close to the sun, then you have an extra bit of electrons that are there that you haven't modeled, right? And that can make your signal redder or noisier. And so by having these additional pulsar noise models and solar wind models, we can really start to disentangle all of this messy astrophysics that our detector is sensitive to. All right, so I thought I was going to talk way over time, but I have not. So we can take some more questions. But to summarize, we've just observed the first evidence of the gravitational wave background, and that tells us that supermassive black holes do in fact merge. Before now, we didn't even really think that that was necessarily true. There were some people who were really adamant that that didn't happen. There's not only evidence in the NANOGrav data that this exists. In fact, I focused on the NANOGrav data because that's the experiment that I work on. But there's evidence for the gravitational wave background in the Chinese pulsar timing array data, in the European pulsar timing array data, and the Parkes pulsar timing array data, and now also in the Meerkat pulsar timing array data. So everyone has evidence for these cross correlations. One interesting feature of the Chinese pulsar timing array data is that they don't have a baseline that's long enough to find the characteristic strain squared. So you remember that that's the amplitude of the background part. But they have the cross correlation part, right? So they can find the Hellings and Downs curve. In fact, they claim to have found a 4.6 sigma between evidence and detection of the Hellings and Downs curve because they have all the cross correlation values. But the amplitude of the background is very low, which means you need to have a long time span. And so if they didn't already know that the amplitude of the background should have been there at those particular frequencies from our internal collaborations, then there's no way that they could have ever published this, right? So you can find evidence for the background with shorter time spans if you know what you're looking for. You find kind of half of the signal. You can find the Hellings and Downs curve, but you can't necessarily constrain the characteristic strain. However, a European pulsar timing array, NANOGrav, and Parkes pulsar timing array found evidence for for both parts of the signal. So what's next? Well, there could be a local nanohertz gravitational wave source next, or there could be something that's at a slightly higher redshift. We'll see. We don't have control over where we detect the next source, but we definitely need a detection protocol. So I've seen some of you at meetings that I organized at KITP and at Aspen, where we tried to have this conversation of what would you need to see in terms of astronomers and astrophysicists and physicists for everyone to agree that there is a gravitational wave signal in pulsar timing array data. And there is no convergence whatsoever. The astronomers can't even agree on how many periods they would need to see in a periodic light curve for it to really be periodic. And so one of the things that we're really working on right now is just trying to establish a checklist. Like, what are the things that are necessary and sufficient? And so far, no one agrees on anything. So this is highly non-trivial, but that's because there's so many moving parts. I think as time goes on and the signals get louder, that there's going to be less contention. But until we get there, I think that it's going to be a kind of fuzzy area for the next 5 years as to what's a real signal and what's not a real signal. Anisotropy is also really interesting in the gravitational wave background. So a cosmological background will likely be much smoother than an astrophysical background. Astrophysical anisotropy is from the shot noise or potentially from large-scale structure, and that's at the order of 10% of the monopole for the shot noise. For the large-scale structure, it's much fainter. And for the CMB, we know it's 1 part in 10 to the 5. So what's next is really everything. Right now we have the background monopole, and that's it. That's all we know. So what's next is the detection of the individual sources, the anisotropy, tracing large-scale structure, measuring Hubble's constant with gravitational waves and pulsar timing arrays, and more ideas that I'm sure that many of you will think of. So thank you all very much for your attention, and I'll take some extra questions. Okay. All right, my friend in the front, number 1. Number 2, is there a number 3? Good, counting to 3 is more difficult.
Like very large number of blobs, like in the future, as if you.
Blobs, there's so many blobs.
Yes.
Yes, well,
Yes.
it's animation.
So what do you assume about knowledge of the pulsar distances in
So the pulsar distances are not super important here because this is a background search. So your pulsar distances might be important for a continuous, like coherent gravitational wave search. When you do the cross correlation of all your pulsar residuals and your pulsars are all at different distances, the pulsar distance terms are not in phase. And so when you cross correlate them, they fade into the noise part of the signal. If you do know the pulsar distances, yeah.
So me and Pulsar, like last week, try to work out how many pulsars you need in order to detect each multipole of the background. And you need like L to the 5 pulsars in order to detect the L multipole, and here it shows that unless you know pulsar distance. But before you know
pulsar distances really don't matter for stochastic background.
So the final map is like L of 100 or something. You will need like 10 to the 10
This is basically an
pulsars.
infinitely well-known map. And Miko, what's the L that you go up to for this map? It's something large.
It wasn't that sensitive, but the L max we used was 8, which was the same as in the detection paper.
No, but like to get to the really fine resolution in this
Oh,
animation.
the resolution, higher than 64, whatever the one above that is.
Right, of n side is 64 at the
Yes,
pixel
yes.
basis. Yeah, so extremely, like basically just imagine it's perfectly.
So you need 10 to
resolved.
10 pulsars to measure.
You don't need 10 to the well. This is an animation. So this is not saying that the angular resolution, depends specifically on these numbers of pulsars. It really depends on the number of pulsar pairs that you have. It goes like NP times NP minus 1/2. You can't have more information than your number of pulsar pairs because the way that you're fundamentally measuring this is with pulsar pairs. I would be so happy to. Okay.
In the NANOGrav data plot,
Yeah.
you have 2 points that are off the curve.
Yes, but I want to just reinforce the fact that those points, these bins, are just for illustrative purposes. This is not a chi by eye situation where you can say that it's 2 sigma or 3 sigma by just looking at the plots. You can make as many bins as you want.
Perhaps my question is, could this be anisotropy or?
So the anisotropies do have a different shape. And so if you're looking at decomposing the background onto a basis of spherical harmonics, you'll get the different looking spaghetti plots, right? And so each one of those will have a different ALM that multiplies the YLM. And so this is largely, this will probably be the dominant one, but you could in fact have some sort of other constraint there. Right now, we don't have any evidence for anisotropy in the background, but we've only gone up to 10 nanohertz.
So with more data, we could expect those to fall into the curve.
I think it would be really interesting to look at that kind of simulation where you have this kind of visual aid for an anisotropic background, but where you've kind of compressed everything into one cross-correlated image. I'm not sure how you would do that, so I'm not entirely sure. But there would be deviations from the Hellings and Downs curve. So it would be, you would have some sort of weight in front of, the monopole, then you have a weight in front of the dipole, the quadrupole, hexadecapole, which is always fun to say. And then you would, sum them all together and get something weird looking. Yeah, so it could come from something like that, but so far there's no evidence of that. Bruce?
I want to ask, you put up some plots where you were talking about cross-correlating large-scale structure with PTA with data.
Yeah.
And as you know, I'm skeptical that just the PTA data alone would be able to see large-scale structure just because of shot noise, but.
Yeah, we've had this conversation a few times.
Right, but if you correlate, then that might well be possible. So I was hoping you could say a little bit more about, just maybe explain the plots a bit more detail.
I'm getting there. Okay, so the plots, this is really, I think there's not a lot of information in this particular figure, given that I didn't think I had enough time to really go into the details. This is really just illustrative to show you that there is large-scale structure, that you would have supermassive black hole binaries in the large-scale structure, and therefore it makes sense to cross-correlate galaxy positions with the gravitational wave background to try to pick out the large-scale structure. Now, if you can detect sources that have strains of larger than 10 to the minus 16, or take some point where you can cut and get rid of them, then you're sensitive to the large-scale structure. So the shot noise is important, and I think we agree on that.
Does that mean detecting a very large number of these sources? I'm not sure quite what that means.
So it means that if you are looking at, I don't have the figure in the slide, but if you can imagine that you have some sort of strain versus frequency and you restrict yourself to the lowest frequencies, you can make a cut at the strain that you want to look at. And then say, I'm cutting any kind of signal that has a strain of larger than 10 to the minus 16, and I look at everything that's underneath that.